them. Okay? Our speaker tonight is Rachel Osten, and her talk is why we need to understand stars to find the next Earth. Looking for planets is not just looking for planets. Upcoming next month, we have a special talk. Okay? If you were here last month, you know that I announced that Tom Brown would be speaking in May. I got Tom to postpone it because we have a special visitor. Sandy Faber from the University of California at Santa Cruz is coming for a special visit, and she has agreed to give a public lecture for us with a most intriguing title, Cosmic Knowledge and the Long-Term Strategy of the Human Race. I think when she says long-term strategy, I think she really means long-term strategy, okay? So you're not going to want to miss one. Sandy is a wonderful person. You really should come and listen to her. In June, we have Nicole Lewis, Probing Worlds Beyond Our Solar System, okay? As you all probably know, at least those of us here in the auditorium, you cannot get to the Space Telescope from the south along San Martin Drive. The south of us is closed until September, so that's still over the whole summer. You'll have to come from the north. All right, and here's a web address in case you need to look that up.
Can you tell them to say that on the signs?
Which signs? I come in from the north naturally, no matter what. So.
Detour.
Okay. I will tell our safety guy that some of our guests have not found the detour signs terribly illuminating, and we'll see what he can that feedback and get back to Johns Hopkins. All right. The website where you can find the upcoming lectures, you can have the link to the live webcast online, as well as the archives once we record these lectures and put them up on our YouTube playlist and on our SDSI webcast. Here are the links here. If you want to sign up for our email announcements, you can do so here. We put this up just about a month or so ago, and the number of subscriptions to our email list has exploded since then. So every day I'm getting new messages of people signing up. So thank you all for signing up. I hope to keep you informed. Announcements. Signing up on our website is easiest, but if you really want to use, you can go to maillist.stsci.edu. It's called Public Lecture Announce. If you would like to contact us, we have an email address called publiclecture@stsci.edu. You can do comments or questions, and yet another way you could possibly sign up for the email list. Social media, if you are on Facebook or Twitter or Google Plus or Pinterest, here are our contact info there. Our Space Telescope feed tends to put up something every day. Myself, for my stuff, I put up maybe one or two things a week if you want to follow my stuff. All right? And because it's such a wonderful night tonight, it may be a little chilly, but the weather is supposed to be permitting. And after the lecture, let's see, right there, I forget your name, hold on. Say it. Duncan, yes, Duncan Watt will take you out. So, Duncan, we're going to meet down here afterwards, as usual. Okay, so if you would like to look through the telescope, it's been a bunch of months since we've actually had the opportunity. Right, and we got a great crowd here, all right? Rachel really draws them in, okay? So if you would like to go up to the telescope across the street after the lecture, meet down here, and Duncan will take you across. All right. So now my segment, News from the Universe for April 2016. Our first story tonight, Journey to the Center of Our Galaxy. And usually, as I say, I like to create fanciful titles for this. Actually, both my titles tonight are taken directly from the press release. This is what we put out in our press release. So our galaxy, when we look at it on the night sky, when you look at it in galactic coordinates, is the Milky Way, this band stretching across the night sky. And in galactic coordinates, of course, the center of the galaxy is in the center of the image. And if you zoom in, well, you can find the constellation of Sagittarius. I can't find the whole constellation of Sagittarius. I can only find this asterism within Sagittarius, which is called the Teapot. Okay? I really don't know what the rest of the constellation Sagittarius looks like. I only know the teapot is part of Sagittarius. And the spout of the teapot points here to where the galactic center is. Okay? The galactic center is in the constellation of Sagittarius. So if you can find the teapot, you can say, oh, look, there's the galactic center. But what do you notice about it? It's dark. Because we're looking toward the center of the galaxy, there's a lot of dust along the way, and it's dark and you can't see much invisible light. So what do? You zoom in and you take a picture in infrared light. This is mid-infrared observations using the Spitzer Space Telescope, and you can see that some of it remains dark, yes, because some of it's really dense dust there that's blocking light, even infrared light, but there is a lot of glow that you can see in infrared light. Now, one problem with Spitzer is that while it has the infrared wavelengths to view in toward the center of the galaxy, it also has a relatively small mirror. Spitzer's mirror is only 0.85 meters, while Hubble is 2.4 meters. And the resolution at a given wavelength is proportional to the size of the mirror. So Spitzer can't see the details in the galactic center as we would like. Hubble does do a bit of near-infrared observations, so Hubble can see a bit more detail. Hubble and Spitzer have previously, in 2009, done an image of the galactic center region. All right, and this is the galactic center area here. This whole region, part of this image is from Hubble, and part of this image is from Spitzer. The high-resolution stuff from Hubble, some of the details are from Spitzer. However, we have a new infrared instrument that we put on in the Servicing Mission 4, Wide Field Camera 3. It has great resolution, so we looked at this region in here really close, and this is your image that we got of the galactic center. Great detail. It's near infrared. All right, and what's really cool about it is, that there's lots and lots of stars. All right, yes, it's full of stars, as the quote 2001. But right here, there is a star cluster, a really, really big star cluster. Let me set your expectations, okay? So we think of star clusters like the Pleiades, right? This is sometimes called the Seven Sisters. However, if you look, you can tell there's a lot more than 7 stars there. The Seven Sisters actually contains about 50 stars. Okay? So some star clusters have tens of stars. Then we have an open star cluster called, I forget the name of it, like NGC 295 or something like that. One of these catalog numbers that you can't always remember. And you can see this one has, perhaps thousands of stars. And then you get to the really big star clusters, the globular star clusters. This one is M13, and this one can have 100,000 stars. Well, the star cluster at the center of our galaxy, this is a zoom in to see the detail, they believe it contains about 10 million stars. Okay? 10 million stars. And so we cannot see all 10 million stars here. This is sort of just the tip of the iceberg, as they said in the press release, that we're just seeing the tip of the iceberg in terms of the incredible number. The stellar density is such as if there were 1 million stars between us and Alpha Centauri. Okay? The nearest star to the sun, if there were 1 million stars in that volume, that would be the density, equivalent to the density of this star cluster at the galactic center. So as I said, we're only seeing the tip of the iceberg. How are we going to see more? Well, we need something with the high resolution of Hubble, but we need not just the near-infrared observations, we need further into the infrared. So as is sort of contractually obligated here, we must note that go from Spitzer in the infrared to Hubble in the visible to the James Webb with a much bigger mirror, keeping and getting even better resolution than Hubble at the same wavelengths, but Hubble resolution well into the infrared. The infrared telescope of the James Webb Space Telescope will be able to do that image and see much more of that iceberg. Even James Webb won't be able to see everything in there because there's just a lot of stuff in the way for seeing this. So that's what is there in the center of our galaxy. And it's much more fun instead of just doing images, you put it into a movie. So this is a movie put together by our outreach staff. There you see the teapot and the rest of Sagittarius there. And as we zoom in, he's going to crossfade to the digitized sky survey, and then to that Spitzer image, and then zoom into that star cluster, and finally to the Wide Field Camera 3 image of the galactic center. All right, question.
How far are we ballpark from the center of our galaxy?
We're about 27,000 light years from the center of our galaxy. We used to think that we're about halfway out in the disk. The disk is about 50,000 light years, about 100,000 light years across. We're just a little more than halfway out in it, okay? Cool. All right, our second story tonight. Here there be monsters. Now, of course, we're used to that phrase related to maps, and if you go off the edge of the map, oh, you get to all the monsters, and the monsters will eat your ships as you fly, or either that or you'll just fall off the edge of the earth, right? Well, we're not talking about those type of monsters, but we are taking a look at the Large Magellanic Cloud. And the same place where there was a monster in that last image, there's a monster in this image. It's a monster of a star-forming region. It is the largest star-forming region in the entire local group, all right, and it's called the Tarantula Nebula. Now, it's not really the monster that I was talking about in the title of it, but in the Tarantula Nebula, there's all sorts of star formation going on, but there is this one particular star cluster called R136. And if we zoom into R136, this is the new image of it, you can see it's not really a monster star cluster, because we just talked about a real monster star cluster at the center of our galaxy, right? This isn't a monster star cluster, but what makes it special is it does contain monster stars. And for this purpose, the monster stars, as defined in the press release, were any star over 100 solar masses, okay? 100 times the mass of our sun. And like, buildings, okay? There are very few skyscrapers. There are a lot of one-story houses out there, right? The biggest ones are few and far between. And for stars, it's even more rare because the biggest ones live for only 10 million years, whereas the small ones can live for billions of years. So these really big monster stars are very rare. You don't find many of them. When they did the analysis of R136, they found the largest collection of monster stars. Now, it's only 9 stars, okay? It's just 9, all right? But that is the largest collection of 100 plus solar mass stars anywhere for astronomers to study. And what's more is that they're all at the same distance in the Large Magellanic Cloud, which gives them a good population for studying these very rare objects. In the Carina Nebula, there's Eta Carina, which is another 100 solar mass star, but it's sort of like the singular one there. Here you've got a collection of 9 of them under study, and it provides a really good laboratory for studying these very rare stars. So here there be monster stars in R136 in the Tarantula Nebula in the Large Magellanic Cloud. Okay, now we go to our featured speaker. And our speaker tonight is Dr. Rachel Osten. She's an associate astronomer here at the Space Telescope Science Institute. And she has been fascinated by stars while she was at, undergraduate at Harvard. Her graduate school was at the University of Colorado, and did postdoctoral fellows at the National Radio Astronomy Observatory in Charlottesville. She has been here for 7.5 years, working on a variety of things, in particular Deputy Project Scientist for the James Webb Space Telescope. So she appreciates the requirement of mentioning JWST in every talk we give here because it is the future of our space astronomy missions here. She uses lots of various observing facilities across the electromagnetic spectrum, and tonight she is going to talk to us about finding planets and studying stars. Ladies and gentlemen, Dr. Rachel Osten.
All right, let's see, is the mic, sounds like it's working? Can everyone hear me? Sure. Okay, good. All right, well, thank you for that introduction. I thought I would take the opportunity to talk to you tonight about an endeavor that astronomers are embarking on now, which is, and we're hoping that, you know, we're obligatorily required to mention the successor to Hubble in all public talks. But astronomers are actually thinking even longer term, maybe not quite as long as Sandy Faber's talk next month, but thinking about what might come after the James Webb Space Telescope. Okay. In the same way that people started thinking about what would come after Hubble shortly around the time that Hubble was launched. That was when the seeds for what became the James Webb Space Telescope were launched. So one of the main drivers for what might come after James Webb is a large UV optical infrared telescope that would be like the grandson of Hubble, probably. But one of the key things that such a large telescope in space could do is find Earth. Okay. There's been a lot of press releases. Or last fall was the 20th anniversary of the first detection of an extrasolar planet around a normal main sequence star, and we've made great strides in finding exoplanets, finding planets around other stars. You know, we are going to, in the next probably 5 or 10 years, have a handful of Earth-like planets that astronomers can start digging into doing detailed characterization of the atmospheres of those planets. And so that motivates these future facilities. But I wanted to take a slightly different, and that's something that, you know, it's not just astronomers who are interested in it. You know, you guys are interested in it. People on YouTube watching this hopefully are also interested. Humanity as a whole, this is one of the fundamental questions that we've always asked ourselves: Are we alone? Right. So I wanted to take a slightly different tack in talking about this subject, and that is thinking about not the planets, but here's that little, in this artist conception, the star behind the planet. And I want to motivate to you why we still need to understand stars. And it's not just studying stars for stars' sake, although, you know, for me, I think that's a perfectly fine reason to study stars. I'm fascinated by stars, as Frank mentioned. But it turns out that when you have a better understanding of the stars themselves, you can use that knowledge to try to find the next Earth. Okay. So, and this might be review for some of you who've come to these public lectures before, but there's many different ways of finding exoplanets. You have to look at stars, right? We have theorized that there might be free-floating planets. No one's detected them yet. All the planets that we found have been found around other stars. And these methods all rely on looking at the star and finding some systematic signal that tells you that there's a very small object orbiting that star. So whether it's astrometry, this technique of seeing, you know, you don't actually see the planet itself, you see the star, but you see tiny wobbles in the position of the star with time that tell you that there is a star plus planet system that's moving, and you can deduce the mass of the planet by how much the star shifts. In the same way, the radial velocity technique, which was the first technique that successfully detected an exoplanet around another star, you're looking at the line of sight Doppler shift of the planet, of the star, as that star plus planet system is moving. Transits, you know, you don't actually see the planet. Again, you see the stellar light, and you see this little periodic decrease in the stellar light that tells you that there's something else there blocking the light out. Another technique called microlensing, where you see a background source, and this is something that Einstein predicted would happen in gravitational lensing. When a star comes between you and that background star, you see a slight increase in the light of the background star due to this gravitational lensing effect. And if that star has a planet, you see a little extra increase in the light of this lensing event, and you can use those characteristics to deduce that there is a star plus planet system. The last of these techniques, it's only one out of these 5 where you actually have to remove the star, right? These other methods, observational methods, you're observing the star plus the planet, and then you're inferring the properties of the planet. In direct imaging, you actually block out the star to try to see the planet directly. You can only do this for, this technique only works for planets that are far enough away from their parent star that you can do that. Our ability to block out the light from the star very, very close to the star has limitations. There are these different techniques of finding exoplanets. You know, the star is involved in those measurements, the fact that there is a star. And this is sort of just eye candy. I am fascinated by this. So this is called the Kepler orrery. These are all of the multi-planet systems that have been found by the Kepler telescope. So these are all detected using that transit technique, okay, where you're just seeing the star and then you're seeing these periodic dips in the light of the star as a planet goes in front of the star and blocks out some of the light. And these are on the, so each little blob that's rotating around is an exoplanet. And there are over 1,700 planets here, around 685 stars. The scale of all of these little individual solar systems is on the same scale as our solar system here, okay? In order to fit them all in on the same plot, they're not all located at the center. And you can see that the planets and the planetary systems that Kepler is finding are very different from our solar system, right? The Kepler telescope, the Kepler mission was designed to try to find an Earth-like planet around a solar-like star. And, you know, it takes the Earth 1 year to go around the sun. So you would expect in a 4-year mission to see exactly 4 transits. So these are very different beasts from from our solar system. And there's one, you know, as compared to the previous slide I showed you, there's something missing here. What's missing? Yeah? The stars. There's no stars here. How could they? These are all the planets. The planets are fascinating. You can see that the temperatures of these planets have, you know, a range of over 1,000 degrees, which is fascinating. But there's no stars there. That's horrible. So I want to talk about why we need to understand stars. Okay, and there's some sort of fundamental stellar parameters that you can use to describe a star. And these are things that are, you know, in astrophysics, usually the more fundamental something is, the harder it is to measure. So there's things like stellar mass, how much does the star weigh, its radius, how big is it, temperature, how hot is it. If you know how big the star is and how hot the star is, then you know how bright it is. Age, we know that our sun is about 4.5 billion years old. We have samples of stars that range from stars that have just been born to stars that are, you know, as old as the age of the universe. Chemical composition, what is the star made of? We know that stars are mostly made of hydrogen and helium, but there's other other elements like oxygen and iron and carbon, which are important to the star, and they're also, since any planet around a star is going, when that planet is formed, it's going to reflect the chemical composition of its parent star. You know, we're made of star stuff, right? The iron in our bones comes from stars. So the star that whose material ends up turning into this planet is going to affect the planet. And then finally, another fundamental stellar parameter is magnetic fields. So over here on the right, I listed sort of some of the implications of these stellar parameters for exoplanets, for understanding planets around other stars. And some of them are sort of very practical things, like the detection techniques that we use to find these exoplanets. We need to know about the parameters of the star so that we know that we're looking at a planet and not a brown dwarf or maybe a stellar binary. So you need to know the stellar mass if you're trying to guesstimate what the planet mass is in radial velocity detections. If you're using this transit method, you need to know what the stellar radius is so that you can figure out what the planetary radius is. If you know the temperature and age of the star, then you can investigate the history of those planets. And in particular, we know that there are populations of exoplanets called hot Jupiters that likely were formed much farther away from their host star than we see them there today, and they migrated. That path of migration, how large it is, how long it took, depends on things like the temperature of the star and the age of the star. The chemical composition of the star gives us clues to the architectures of planetary systems. And then the star's magnetic field, and this is actually what I'm going to spend most of the rest of the talk talking about. The star's magnetic field helps to set the environment for planets and ultimately for life. So we need to understand the star if we want to understand the planets and ultimately life. Okay. So when I say why we need to understand stars to find the next Earth, I don't mean just any old Earth. I mean an Earth like us, right? An Earth that could support us. And this is a graph that astronomers use to describe particularly interesting places in space. So space is vast, but if you want to find an Earth, not every piece of space is as interesting as other pieces of space. So if you want to find another Earth-like planet around a sun-like star, you would look here at 1 and 1, right? So this is where the Earth is right now, and the Earth, our Earth, orbits around a sun-like star. Astronomers define this region of space called a habitable zone. Okay, and it's got a complex definition. I'm not going to go into, I don't even know what the entirety of the definition is, but it's basically, where do you need to be located with respect to a star so that you can have liquid water on the surface of a planet? Okay. It's nice that these calculations show that we're in the habitable zone of our sun. That's good. Yay. Theory works out. But if you look at more massive stars than the sun, those more massive stars are bigger, they're hotter, they're going to be much brighter. So you need to be located further away from, if you're a planet and you want to be habitable, you got to be located further away from your host star. On the contrary, if you're looking at planets around dim little red dwarfs, they're small, they're cool, so they're not as hot, they're not as bright as the sun. So if you want to have liquid water on the surface of an Earth-like planet around an M dwarf or red dwarf, you need to be much closer to that star in order to be potentially habitable. Okay. So in astrophysics, lots of things go down by 1 over distance squared, right? Gravity goes down, the luminosity goes down by 1 over distance squared. When you are closer to the star, you're going up by 1 over distance squared, right? You're getting closer. Stellar effects dominate as you get closer and closer to the star. So it's not just that for dim little red dwarfs, you need to be closer to the planet to have liquid water on the surface, suddenly anything that star is doing, you are feeling, by, a factor of 10 or so greater, right? 1 over distance squared. So that's actually more like 100 times. You're feeling that effect to a much greater degree than you would if you're sitting in an Earth-like planet in the habitable zone around a sun-like star. Okay. So that star's magnetic field helps to set the environment for planets and life. I should just sort of mention, and maybe I should have mentioned this at the beginning, sort of one of the interesting things about my research is that it's a very interesting integration of studying stars and studying our sun, which is actually unusual amongst astrophysicists. Even though the sun is a star, it's an astrophysical object. It is often not studied as an astrophysical object by astrophysicists. When we look at the sun, this is a picture of our sun with the top half sort of peeled back so that you could look inside the sun and see what it looks like. And then the bottom half of this just shows some of the ways that we see that the sun has a magnetic field. And these are similar things that we can use to look at other stars to deduce that they have a magnetic field. So the sun has sunspots, which is where tubes of magnetic flux poke through the surface. We can see them because they're slightly darker than the surrounding region. These magnetic fields that poke up through the surface heat plasma to temperatures that are in excess of the sun's visible surface. The sun's visible surface has a temperature of 6,000 degrees. And you can see material that is heated to temperatures of 10,000 degrees, 50,000 degrees, 100,000 degrees, 1,000,000 degrees above the surface of the sun. And those are layers of the sun's atmosphere called the chromosphere and the corona. The sun can also do crazy things like loft this cool material that is slightly hotter than the visible surface of the sun, but have it basically levitate it above the surface of the sun. And it can only do that because a magnetic field is there, basically invisibly holding up this prominence material and keeping it there. If the magnetic field weren't there, that material would slam down into the surface because it has no right to be hanging out at high heights above the surface of the sun. And this is all due to the fact that when you look inside the sun, we see that there's a core where nuclear reactions are taking place. That's what powers the light of the sun. That energy travels first by radiation and then by convection out to the surface where we eventually see it as the visible light of the sun. Solar physicists know that the interior of the sun, this radiative zone, rotates like a rigid body, rotates basically like a basketball. The convection zone, however, has a different rotation rate depending on where you are. If you're at the equator, there's one rotation rate. If you're up at the pole, the North Pole or the South Pole of the sun, there's a different rotation rate. The sun actually rotates faster at its equator than it does at its pole. This is a result of differential rotation, which is produced because the convection zone has this differentiated rotation. And at the interface between these two regions, there's a slippage. There's a difference in velocity between the material that's part of this radiative zone and the material that's part of this convection zone. And that is thought to be where magnetic fields in the sun are created. And you guys have probably all heard of the sunspot cycle. The sun has an 11-year cycle of sunspots. If you were to go out every day and count the number of spots on the surface of the sun and do that over decades, you would see a pattern emerging that has a period of about 11 years. We are in the waning phase of the current solar cycle. So those are some of the different ways that we can see that the sun has magnetic fields. And we can also use many of these techniques for seeing that stars like our sun also have magnetic fields on their surfaces. Okay. All right, so that was a big long digression about stars, and some of you are probably here to think about, okay, planets. I want to hear about planets. So here's another schematic that sort of puts that into perspective. Here's the sun. This is not to scale. So the sun has a magnetic field, but the Earth has a magnetic field, right? And it's that interaction between the sun and between the Earth and the balance of what the sun can do, what the sun can throw at the Earth, and how the Earth can react that helps to set the environment for planets and for life. And so this comes in a couple different forms. The star's magnetic field can heat plasma to temperatures up to several tens of millions of degrees. That's this chromosphere and corona that I told you about. The star's magnetic field also expels material. Okay, the sun has a wind that is a steady, more or less steady stream of particles leaving the sun. That, they're particles. They can hit things. They can do things. This material can get expelled in sort of a steady manner. That's a sort of steady wind. The sun also belches, these things called coronal mass ejections, which happen during a space weather event, which I'll talk about. That also impacts the Earth. The third flavor of this interaction is that the star's magnetic field can accelerate particles to very high energies, to MeV or GeV energies. This is nature's accelerator. It's not quite as good as the LHC, but we didn't have to spend billions of dollars to build the sun. So I'm going to talk about how each of those three things, the things that are due to the fact that the star has a magnetic field, and how we need to understand those things if we want to understand life. Okay, so we're back to planets again. Okay, this is a spectrum of the Earth. Okay, and this is something that astronomers use when we talk about the types of signatures in a spectrum of a planet that you would need to see to infer that there's life. Okay. This is a term that's called biosignatures or biomarkers. Right? These are things that you can. So if you just take an image of an exoplanet, that can give you some information about its temperature, maybe its age, if you have some other constraints. But when you want to find Earth, when you want to find another Earth, you need more than just a temperature, because there's many things that could have the same temperature. That just doesn't mean that there's life on it. You need to take a spectrum. You need to take a spectrum of that planet. And hopefully you would see a spectrum something like this. We have such a spectrum of one planet, right? The quest is to try to find a spectrum of another planet and be able to, based on this spectrum, be able to say, yes, there is life there. Nature, as you've probably have guessed if you've gone to some of these talks before, nature is very inventive. Nature is very creative. Right? There's a quote from Shakespeare: "There's more in heaven and earth, Horatio, than are dreamt of in your philosophy." Right? There's more than one way you can form some of these signatures that doesn't require the presence of life. So if you're looking for a spectrum, you want to be absolutely sure, or as sure as you can be, that those signatures that you're seeing are coming from life, or that you understand the processes that are forming these signatures. So things like carbon dioxide could suggest possible volcanic activity, could not. There are other ways to make carbon dioxide. Methane could indicate the presence of anaerobic bacteria, could not. Hubble has actually seen exoplanets that has seen methane signatures in exoplanets. That's not the smoking gun of there's life. Water vapor suggests habitability. We've actually seen many planets now that have some kind of water haze in their atmosphere, but that alone is not a smoking gun telling you that you've got life. There's other things like this vegetation jump tells you that there's plants. The blue of the sky at shorter wavelengths tells you how much atmosphere there is. And other signatures like oxygen and ozone. Ozone is often pointed as a possible biosignature because in our early terrestrial atmosphere, it was this complicated interchange of the first components of life to form that changed the Earth's atmosphere and actually started producing oxygen and ozone. And so that's one possibility of looking for a signature that might be a biosignature. However, as I mentioned, nature can be very creative. There are other ways to form almost all of these signatures that do not involve the presence of life. And in fact, there's some very interesting research recently by scientists using the Hubble Space Telescope who have shown that you can actually produce oxygen and ozone in a planet without needing there to be life. So the radiation from the star, which is produced by the magnetic fields from that star, the amount of ultraviolet radiation that the star produces can actually, the specific ratios can actually affect how much of these signatures are formed. Okay. And so this is just a schematic from one of these recent papers that there's a detail here about just what kind of radiation is hitting the star, hitting the planet, and then what's happening. Hydrogen is escaping. There's lots of complicated stuff going on. But these ultraviolet photons and X-ray photons from the star originate from the star's magnetic fields. And it is not a simple thing. We can't just predict what those levels will be. They do depend on some things like how old the star is, what the star's rotation rate is, what its sort of general magnetic activity levels are. But we haven't gotten to the situation where we can make precise predictions of what a star's ultraviolet and high energy radiation fields should be for sun-like stars and cooler, so that we can just have that be a knob in some models. So we need to understand the stars a little bit better, and that means understanding the magnetic activity of the stars in order to make progress in that area. So that's one area. There's also the stellar wind that I mentioned, and this is actually some results that were obtained for observations of our sun by this satellite called the Ulysses satellite that actually went around the sun. It went above the plane where all the planets are in and made these measurements, and then dipped down below the plane where the planets are in, made measurements in the southern part of the solar wind coming off the southern part of the star, of the sun. And you can see that there is a difference. The sun is a very fast solar wind that has speeds of several hundred kilometers per second, 600-700 kilometers per second. At the equator, it drops down. That has to do with the fact that the magnetic structures that you tend to see at the north and south poles of the sun tend to be open, so they can accelerate particles, and they have a higher velocity. The magnetic structures that you see at lower latitudes on the sun tend to be closed magnetic structures, so that affects the overall velocities of the material that's leaving. We also know that the sun's mass loss, the amount of material that's leaving the sun in the solar wind, is very, very tiny. So over the roughly 5 billion years that the sun has existed, if we assume that the mass loss rate of the sun that we know it as we know it today, that it was constant over those last 5 billion years, the sun will have lost 1/10,000th of its present mass. It's a very feeble wind. Turns out to be important. I mean, I'll show you some examples. We are pretty sure that other stars like the sun also have these winds, but we have not detected them. Okay. So why is it important? The solar wind interacts with planetary magnetospheres. This is an example from a result from a couple of years ago, looking at the planet Mercury, which of course is the closest solar system planet to the sun. And the solar wind may have prevented Mercury, the planet Mercury, from forming its own strong magnetic field. There's a feedback and a coupling between the stellar wind and the ability of a planet to form a magnetosphere. Okay? So this is something that we think we might have evidence of this having happened at Mercury. We also have inferences, modelers taking these results and sort of extrapolating to much larger regions of parameter space for what kinds of exoplanet distances from the host star and what kind of parameters of the stellar wind, where you might have a situation where that exoplanet might not be able to sort of stand its own on a fight between what the star is doing and what the planet is trying to do. So there's another area where we really need to understand the stars and how those stars are losing mass so that we can understand the magnetic field, how that affects the magnetic field of a planet, since that's going to be important to being able to form and sustain life. So I mentioned that these winds are very feeble. We do not have any direct measurements of stellar mass loss. There's a very ingenious astronomer by the name of Brian Wood who's used the Hubble Space Telescope to make indirect measures of stellar mass loss by basically looking at signatures of excess absorption along the line of sight from us to a star and inferring that that's actually coming from right next to the star, and it's coming from this little bit of stellar wind in our line of sight that's eating away some of the light of the star. So there's the sun. Down here we see that it's possible that stars that are much more magnetically active than the sun might have an increased mass loss rate. That would make sense with some of the sort of hand-wavy understanding that we have of how magnetic fields couple to mass loss and production of hot plasma that we see in the X-ray. But it's indirect. It's all indirect. We're also finding, so the universe is very creative. This is an artist's impression of a host star and its exoplanet. This is a Neptune-like exoplanet orbiting around an M dwarf. This star is not a good planet host. So, as I mentioned earlier, planets around M dwarfs have to be much closer to the host star in order to be in this habitable zone, the sweet spot where the planet might be able to have liquid water on its surface. And when you're much closer to your parent star, you feel the effects of the star. So even though this is a feeble red dwarf, the radiation from that star is actually bleeding off hydrogen from the atmosphere of the exoplanet. And you can see this, it manifests the inferences, it manifests in the inferences as a large comet-like tail coming off this exoplanet. You can also get the same kinds of effects, maybe not quite as large, by having a stellar wind interact with the planet's atmosphere and basically, just like a comet, sucking material off the planetary atmosphere. And that's as a result of the magnetic fields that's heating plasma, that's expelling material. So the other topic I want to talk about are something that we know from the sun, from studies of the sun, are called solar eruptive events. Okay, and they have three components. This is one of the nice when I give talks. Most stars are points of light. They don't make very interesting pictures by themselves, just a single dot in a field of view. So I like to show pictures in movies of the sun because they're fantastic, they're dynamic. I mean, these are movies. These are actual images of the sun made with the Solar Dynamics Observatory. And I mean, I could just sit and eat popcorn and watch these all day. They're fascinating. So here is what the sun looks like if you had X-ray eyes, and you can see that it's highly structured. This structure is all coming about as a result of magnetic fields poking up above the surface of the sun. And you can see over here on the limb, there's some structures that are getting brighter with time, and you can see that they're loop-like structures that are rearranging themselves over the course of the hour or so that this movie takes place. That's a solar flare. So those are photons that are heated by the magnetic fields. They're heated on a very short time scale, so you see this sudden increase in brightening. That solar flare is accompanied on a much larger scale by this coronal mass ejection, which is the magnetic field of the sun getting blown out as this material is being expelled from the surface of the sun. The scales here are much larger. This is the disk of the sun. All right, so this is about 1 solar radius above the surface, the visible surface of the sun, and this goes out to tens of solar radii. I mean, the coronal mass ejections will even show you hit the Earth. So this is the coronal mass ejection that corresponded to the previous flare. When you see large flares on the sun, they are almost always accompanied by these large ejections of mass. Okay. And this is a different event, but this is particularly dramatic, so that's why I like to show this. You see that fuzz? That's not static, that's not noise. That's what happens when these very energetic particles slam into your satellite. And you can see, like in the very beginning of the movie, you can see what looks like a coronal mass ejection. There is a coronal mass ejection. And then, mere seconds later, this spacecraft is much closer to the sun than we are. This spacecraft intercepts those very energetic particles. Those energetic particles can be bad. Okay. So from the perspective of us here on Earth, we are interested in these solar eruptive events because they are what's called geo-effective. Okay? If they hit the Earth, they can do damage. And that's what this movie is showing, that one of those coronal mass ejections coming towards the Earth, and you can see the magnetic field lines of the Earth moving around, moving close to each other and reconnecting. And for a moderate event, that's basically what produces aurorae. You're seeing energetic particles streaming down the magnetic field lines of the Earth and lighting up this auroral oval in the northern and southern hemisphere. So that's space weather. Space weather dialed up many notches is habitability. It's a habitability concern. This geo-effective part of the eruptive event is basically the coronal mass ejection and those energetic particles. You can see a flare from any part of the visible surface of the sun. And you can, if you block out the disk of the sun, you can see these coronal mass ejections. Whether those, and the photons from the flare will hit you because they travel in any direction. There's no preferred direction. The CMEs and the energetic particles have a constraint, And that is illustrated here by these magnetic field. These are lines of magnetic force extending out from the surface of the sun. Since the sun rotates, these are sort of like a ballerina's skirt, if you will. She's twirling around. So these coronal mass ejections and energetic particles have to follow those magnetic field lines. And if the location on the surface of the sun happens to just line up with, following a magnetic field line and hitting the Earth, then we're in for problems. And there are modelers down the street at Goddard Space Flight Center who do this for any kind of event that happens on the sun. They can determine what the likely impact is for us here on Earth, for any of the other planets in our solar system. I actually was just reading a result about how the New Horizons spacecraft was making measurements of space weather out beyond Pluto in environments where we don't really have many constraints. So the flares are easy to see. The CMEs and the energetic particles are the ones that you actually have to worry about. They're all ultimately related to each other. As I mentioned, it's an eruptive event is composed of a flare, a coronal mass ejection, and these energetic particles. The energy ultimately comes from the magnetic field in the sunspot or active region that's powering that flare. And one question that solar physicists have asked is, how big of a flare can the sun produce? That's important for us, right? Because we have things like spacecraft, GPS satellites in orbit around our Earth, and what I showed you was happening to that one sun-observing satellite could happen to any of those spacecraft. In fact, a previous Japanese X-ray astronomy satellite to the one that met its demise a couple of weeks ago experienced one of these space weather events, and it killed the satellite. It experienced a year's worth of radiation in 24 hours, and it went belly up and said, ah! So how big of a flare can the sun produce? The biggest ones that we've seen have energies of about 10 to the 32 ergs in these funny units that astronomers like to use. When we look at flares on stars, we see that they can be up to 1 million times larger. So there's a lot of parameter space there between what our sun can produce and what the extreme stars, extreme red dwarfs, extreme stars in binary systems can produce. And based on based on some models about the interaction between magnetic fields and sunspots and the amount of energy that can be produced, we think that we haven't observed any. We're not significantly off from the maximum the sun can probably maintain, can probably produce. So we're likely safe, but it's those other stars I worry about. It's those other planets that I worry about. Okay. So how do flares and these associated events affect habitability and space weather? So I've told you that a potentially habitable planet around an M-dwarf star is going to be much closer to its parent star. And so you might be thinking, well, that seems kind of odd. Why wouldn't you just look at solar-like stars? Because they're further away, and we might still have to worry about some of these issues, but we wouldn't have to worry about some of the other issues. Well, it turns out that M dwarfs are a dime a dozen, literally. You can't go anywhere in the solar neighborhood without stepping on an M dwarf. So they're very numerous. If you want to increase your chances for trying to find a potentially habitable planet, you need to have lots of potentially habitable planets that you can pick from, because we also know that in astronomy, odds can be astronomically small. So if you want your odds to be at least one, you've got to start out with a lot of stars and planets. So looking for planets around the most numerous type of star in the galaxy is a good way to start. It's also true that planets around M dwarfs are relatively easier to see because the star is less massive. The planet has a planetary mass, right? That's not really changing by all that much. But that ratio means that it's slightly easier to find planets around M dwarfs than it is to find planets around solar-like stars. They're going to be rotating or orbiting around their planet, around their star, much closer, so you have many orbital periods that you can try to look for. So things get a lot better. However, when you've got a planet that's very close to its star and it's feeling the effects of that star, you have some problems. These planets are going to be tidally locked to their star, just like the moon is tidally locked to the Earth. The moon has the same rotation period, as its orbit. That means that any planet is going to have a very weak magnetic field. So it's not going to be able to protect itself from flares and coronal mass ejections as much as, say, our Earth is, because we're much further away from our parent star. M dwarfs, we also know, have a very high flare rate. They tend to be very magnetically active. And if those very energetic flares are accompanied by coronal mass ejections like we see on the sun, that could be a big no-no. That could be potentially disastrous. The one caveat is that we haven't actually measured this yet. We haven't measured the rate of coronal mass ejections from M dwarfs, and I'll talk about that in a little bit. So the other thing that I mentioned was that these eruptive events produce energetic particles. Okay, this is a result of a paper from a few years ago that looked at the astrobiological effect of an M dwarf flare. And they found that if they put an M dwarf, a planet, an Earth-like planet, around an M dwarf in the habitable zone of the M dwarf, and then shot off one of these flares that have been observed, and then looked at the impact in the ozone layer of that terrestrial planet, the flare itself was fine. It didn't do any damage. That decreased the amount of ozone in the atmosphere of the planet, but only by 1%. So that's recoverable. That's not going to be a huge impact. However, when we look at this stellar flare and we take our knowledge from solar flares and the accompanying energetic particles that follow those solar flares and scale that up to what we see from the stellar flare, and then put that into a model and try and look at the impact of the flare and the energetic particles on this Earth-like atmosphere, things are very different. Okay, so the ozone layer of this previously potentially habitable exoplanet around an M dwarf, the ozone layer goes away. It takes about 2 years, but the ozone layer is completely depleted from the atmosphere of this hypothetical planet, and it takes 50 years to come back. That's not good. That's not good if you're living on that planet. Okay. So here's the thing. We can see stellar flares. That's the basic, most of what I've spent my research career studying is studying stellar flares. We cannot at present see those stellar coronal mass ejections or the energetic particles. And it's those things that turn out to be the most important to characterize if we want to get a sense of what kind of stars and the planets that are around those stars are potentially habitable. We need to have measurements of the stellar wind. We need to have measurements of these coronal mass ejections and energetic particles in order to be able to say, yes, this is a good candidate for taking your 16-meter space telescope and observing at this one star for 50 hours to try to see that spectrum that I showed you. So for now, these astrobiological investigations of stellar flares take what we know about the sun and then they extrapolate by orders of magnitude. And we really don't know if the physics is the same. And so, I mentioned this a couple times. The universe is creative. We've got some surprises in store, even in our own backyard. I told you that most large solar flares have large coronal mass ejections. Well, never say never. In 2014, there was a very large active region on the sun, right here, which is almost as large as Jupiter. And it produced many large flares, but it did not erupt, did not have any coronal mass ejections. Solar physicists, and this is a movie of one of those events. Solar physicists are trying to, they have very detailed probes of their events. They're trying to understand how this can happen, and we stellar astronomers can then take that knowledge and apply it to other stars, and try to see if that's something plausible that could be happening around other stars. So it's all well and good to take the detailed observations of the sun, but we'd like to confront observations with real observations of those stars, not just the sun, and assume that all stars act like the sun, because that's not necessarily the case. We're just starting to explore whether we can see stellar coronal mass ejections in a systematic way. So people have made claims, astronomers have made claims before that they saw some transient ejection of mass from a star. And it was always kind of a weird flare. All right, they saw some increase in the light of the star, but it didn't look like your standard textbook solar flare, stellar flare. There was something a little different about it. And so the astronomers would scratch their heads and do some calculations, and they would say, oh, maybe there was a little bit of mass that got ejected, and then we're seeing it in this, we're very clever, and so we're able to infer that there was this coronal mass ejection happening. But if you want to do this kind of a study, if you want to explore parameter space and be able to know what kinds of stars produce coronal mass ejections, what kinds of stars don't, you need to have something that is a more systematic way of detecting coronal mass ejections than just getting lucky, right? It's nice to be lucky, but that doesn't give you that fundamental knowledge that you need. And so we're just now starting to explore whether we can see stellar coronal mass ejections in a systematic way. And we have to use, the best bet right now is to use radio telescopes. This is a low-frequency radio telescope that has been built mainly in the Netherlands, but it's basically has a network of stations that are placed around Europe, even into England. Doesn't really look like what you think of a radio telescope looking like. These are very low frequencies. These are FM wavelengths, basically. So. And you might ask, well, wouldn't you be detecting radio stations? And yes, you will. You do detect radio stations, but if you do very clever ways of obtaining your data at high enough time resolution and high enough frequency resolution, you can basically mask out the radio stations and look for extraterrestrial signatures. This is, hopefully someone recognizes this telescope. Yes?
It's a very large array in the plains of San Agustin, central New Mexico.
That's right. I have one correction. It's now called the Jansky Very Large Array.
Oh, is it?
Yes. But yes, you're right. So this is a Y-shaped array of 27 radio dishes in the plains of San Agustin, New Mexico, that can also listen to the universe at low radio frequencies and can potentially see these signatures. And when I say that we're looking for these signatures, this is the sort of signal that we're looking for. So this is something called, you guys have seen, I showed you a spectrum. You've maybe heard about breaking light up into wavelengths or frequencies. This goes a step further in the complication chain. This is breaking light up into frequencies and time. Okay, this is called the dynamic spectrum. When you look at low frequency radio bursts, this is actually from the sun. You see that there are very specific signatures. This is something called a type 2 radio burst. So this starts at very high radio frequencies, 700 megahertz, and then it drifts to lower radio frequencies. That characteristic shape is a result of a shock that's formed by a coronal mass ejection passing through the outer atmosphere of the sun. We can predict what this shape will look like on other stars where we know or we have measurements of their coronal magnetic fields and temperatures and densities. And so we can start to look for this as a systematic tracer of coronal mass ejections. And I have a project that's funded by the National Science Foundation. I have a graduate student who's poring over lots of radio data, trying to find these sorts of signatures in nearby stars so that we can say that, yes, these very active M-dwarf stars also have coronal mass ejections, just like the sun has flares and coronal mass ejections. However, things can get interesting. So I showed you before these large solar flares without coronal mass ejections. This is a schematic of these arcades of loops on the sun, coronal loops, and a coronal mass ejection. It is possible. I'm not really a betting person, but it's possible that this search, trying to find solar coronal mass ejections, we might not find anything. I have tried to tell that to my graduate student, so he won't be completely disappointed if he spends several years mining terabytes and terabytes of data and he comes up with a null result, which is still interesting because it means that these large-scale magnetic fields may prevent breakout and may prevent eruption. So it may tell us that these stars really aren't just scaled up suns, scaled up flare producers. And this is an example from a recent paper of a host star and a hot Jupiter, and some modeling that these folks have done, showing the possible interaction of the magnetic fields of the planet with the magnetic fields of the surface of the star, that may provide an even more complex interaction between the star and its planet. That is another avenue to consider. So with that, I'll stop and I'll take questions. And if you want to come back in maybe 20, 30 years, I'll be able to tell you whether stars have coronal mass ejections, whether they're going to prevent us from finding life, and whether the spectrum of the first habitable exoplanet is affected by space weather. Okay, thanks.
Does our sun undergo the wobbling phenomena you described earlier? And if so, what sort of frequency and magnitude are we talking about? I've never seen it wobble.
Oh, you wouldn't. The astrometric wobble of the sun due to, Jupiter is the biggest. It would be tiny.
I'm sorry?
It would be tiny.
Right. Matter of fact, one of our metrics
a reliable guide in your first slide to find other planets if we can't even see it in our own sun.
Well, you have to remember that when you've got a Jupiter that's not at Jupiter's distance from its host star, but is at Mercury's distance, or even the Earth or Mars's distance, that shift is going to be much larger. And I don't think we have made any direct measurements of exoplanets due to astrometric shifts, but you know, the precision that we're getting to is pretty remarkable.
The first slide you showed where all the stars were wobbling, and I'm guessing those were not based on the effect of an exoplanet, they're based on giant planets, is that?
No, some of those are giant planets. Some of them are Neptune size or super Earth size, but they're very close to their planet, their host star.
And those
those were detections made using the transit technique. So they're very tiny, you know, parts per million decreases in the light of the star as the planet goes in front of it.
Right. Let's just be clear. We don't actually see that wobble. That is the wobble that we interpret from seeing either the transits or their radial velocity technique or other techniques to detect the planet, and that's a graphic to illustrate those orbits.
On a different time scale.
Yes.
Yes.
And on a totally different time scale. Yes.
Are you more likely to find CMEs being blown out from larger stars rather than these dwarf stars that you're?
Well, I mean, it's an interesting question. People, so we know that for stars that are about 20% more massive than the sun, if you go beyond that, if you go more massive than that, those stars do not have an outer convection zone. So if they're producing magnetic fields, it's going to be by some completely different mechanism. When you go to much smaller stars, these red dwarfs that have, you know, a third the mass and a third the radius of the sun, they are producing flares once every couple hours with energies that are 10,000 to 100,000 times more energetic than the biggest solar flare.
Is that more active convection zone? Is that?
They have very deep convection zones. And some of these objects, the convection zone goes all the way to the radiative core. So they are able to be vigorous and efficient producers of magnetic fields, and we see that in the flaring. We see other evidence like signatures of heated plasma that's produced outside of flares. Just based on statistics, right? You've got the potential a lot more stars, a lot more M-dwarf stars, potentially a lot more planets that you can detect, and also a lot more flares that you can detect. So it may be that these very active M-dwarfs have very strong, large-scale magnetic fields that would prevent coronal mass ejections from happening. So you might see flares aplenty, but it's just photons. You're not seeing that expulsion of matter. And it's possibly paradoxical that lower magnetic activity stars might be able to produce both flares and coronal mass ejections like we see the sun can produce most of the time.
What are the energetic particles? Are they like helium nuclei and stuff like that, or?
Yeah. They're highly energetic ions that have energies of MeV to GeV energies. Yep.
Could you please expand on what is meant by vegetation jump as one of the things to infer the possibility of?
I can't expand very much. Here, where we go. So that is, so that refers to this bump in the spectrum that I don't know much more than what's on the slide, but it's a characteristic signature that is seen in our spectrum of our Earth. It's presumed to come from the presence of plants, green plants.
They seem to be tied in with the oxygen there.
Well, that just means they're forming in the same relatively close by in wavelength. Doesn't necessarily mean that.
Way in the back, I saw a hand.
Yep.
You mentioned that planets' habitability is a function of the size of its sun and relative distance.
Mm-hmm.
So is there like maybe like an algorithm or a statistic used to determine like, oh, we found this solar system. The chances of finding a habitable planet are, they have something like that? Or?
Yes, they do. They do. So the most popular method for finding exoplanets these days is the transit method. From that, that Kepler orrery that I showed you kind of gave you a sense of how many thousands of exoplanets have been detected. But basically, once astronomers find an exoplanet or infer the presence of an exoplanet, they plunk it down on this graph. And then they say, no press release. Yep, press release.
Other questions?
It seems to me like, besides the habitable zone, the mass of the planet, how the surface gravity would be very important. I wouldn't want to be on a 10G surface,
Yeah, that's true. That's true. The mass of the planet will be important. The mass of the planet might be another factor that you would need to consider when thinking about how the planet can construct its own magnetosphere. And maybe planets that are slightly more massive than the Earth might be able to produce a magnetosphere that can protect itself from the influence of that host star, even though the planet is in a habitable zone and is 5 to 10 times closer to the star. That might slightly negate the tidal locking weak magnetic field.
Senator.
When you say like the water vapor signature, what exactly is the signature? What are you reading or picking up that tells you that there might be water vapor around a planet many light years away?
There we go. So when we look at the light of a planet, the water feature, where's the water feature? Here's the water feature, is particular wavelengths of light that have been absorbed as a result of the presence of water. Okay, so water has a very specific molecular structure. It can only absorb the light of the planet at particular wavelengths. So when you see a water feature, what you think might be a water feature at one particular wavelength, you instantly know where the other water features will appear in the spectrum. And so you can see here there are 1, 2, 3, 4, several of these things. So you see a decrease in the light when you break the light up into wavelengths. You see a decrease at a particular wavelength that you know is formed from the presence of water being in the atmosphere and being able to remove material at those specific wavelengths.
Is that all visible spectrum or UV, infrared?
This is the ultraviolet visible, and this stretches into the infrared.
Okay, last question because we're approaching 9:30 and that's my cutoff time.
Your array of planets versus the habitable zone, are those thought to be relatively stable since you have a lot of types of planets? Is there any thought that there might be migration?
These are our planets. These are the planets in our solar system.
Right.
Okay. There almost certainly is migration taking place. So when some of the first exoplanets that were discovered were these things that we now call hot Jupiters. It was very surprising that you were finding something the size of Jupiter at the distance of Mercury, away from its parent star. We now understand that can happen because the planet actually formed much further out from the star and then migrated inward, and then something stopped it from continuing to migrate into the star itself and getting swallowed by the star. So that migration, as I mentioned earlier, will depend on the age of the star plus planet system. It will depend on the temperature of the star. So astronomers can make predictions about, based on where you find a hot Jupiter, where it might have actually been formed. It probably wasn't formed at this close in distance to the parent star.
Right, and I think one of the things we can take away from your talk is that we often think about these things about what planets can form where and where the planet is, but what your talk really emphasizes is that there are even more variables when you consider the types of stars, and that the red dwarfs may be the most abundant types of stars in the universe, but if they have all of these, if they have too much activity, they're still not a wonderful place to form a planet around, or at least an Earth-like planet.
And people often think, oh, M dwarfs, they got lots of flares. You don't want to be on a planet around an M dwarf. But my research might actually show that that's a perfectly fine place to be.
All right. Duncan is going to come down here. If you would like to go to the observatory across the street with Duncan, please join him here. And let's give Rachel one more big hand.
Thank you.
Thank you. Had a very, very active online chat.
Yeah?
There were people chatting throughout the entire thing.
Okay.
Some of it, you can see.
Oh, wow.
I was answering questions all during the talk. So yeah. We have an email address called publiclecture@stsci.edu. You can do comments or questions, and yet another way you could possibly sign up for the email list. Social media, if you are on Facebook or Twitter or Google Plus or Pinterest, here are our contact info there. We our Space Telescope feed tends to put up something every day. Myself, for my stuff, I put up maybe one or two things a week if you want to follow my stuff. All right? And because it's such a wonderful night tonight, it may be a little chilly, but the weather is supposed to be permitting. And after the lecture, let's see, right there, I forget your name, hold on. Say it. Duncan, yes, Duncan Watt will take you out. So Duncan, we're going to meet down here afterwards, as usual. Okay, so if you would like to look through the telescope, it's been a bunch of months since we've actually had the opportunity. Right, and we got a great crowd here, all right? Rachel really draws them in, okay? So if you would like to go up to the telescope across the street after the lecture, meet down here, and Duncan will take you across. All right, so now my segment, News from the Universe for April 2016. Our first story tonight, Journey to the Center of Our Galaxy. And usually, as I say, I like to create fanciful titles for this. Actually, both my titles tonight are taken directly from the press release. This is what we put out in our press release. So our galaxy, when we look at it on the night sky, when you look at it in galactic coordinates, is the Milky Way, this band stretching across the night sky. And in galactic coordinates, of course, the center of the galaxy is in the center of the image. And if you zoom in, well, you can find the constellation of Sagittarius. I can't find the whole constellation of Sagittarius. I can only find this asterism within Sagittarius, which is called the Teapot. Okay? I really don't know what the rest of the constellation of Sagittarius looks like. I only know the Teapot is part of Sagittarius. And the spout of the Teapot points here to where the galactic center is. Okay? The galactic center is in the constellation of Sagittarius. So if you can find the Teapot, you can say, oh, look, there's the galactic center. But what do you notice about it? It's dark. Because we're looking toward the center of the galaxy, there's a lot of dust along the way, and it's dark and you can't see much invisible light. So what do? You zoom in and you take a picture in infrared light. This is mid-infrared observations using, it's a monster of a star-forming region. It is the largest star-forming region in the entire local group All right, and it's called the Tarantula Nebula. Now, it's not really the monster that I was talking about in the title of it, but in the Tarantula Nebula, there's all sorts of star formation going on, but there is this one particular star cluster called R136. And if we zoom into R136, this is the new image of it, you can see it's not really a monster star cluster, because we just talked about a real monster star cluster at the center of our galaxy, right? This isn't a monster star cluster, but what makes it special is it does contain monster stars. And for this purpose, the monster stars, as defined in the press release, were any star over 100 solar masses, okay? 100 times the mass of our sun. And like, buildings, okay? There are very few skyscrapers. There are a lot of one-story houses out there, right? The biggest ones are few and far between. And for stars, it's even more rare because the biggest ones live for only 10 million years, whereas the small ones can live for billions of years. So these really big monster stars are very rare. You don't find many of them. When they did the analysis of R136, they found the largest collection of monster stars. Now, it's only 9 stars, okay? It's just 9, all right? But that is the largest collection of 100 plus solar mass stars anywhere for astronomers to study. And what's more is that they're all at the same distance in the Large Magellanic Cloud, which gives them a good population for studying these very rare objects. In the Carina Nebula, there's Eta Carina, which is another 100 solar mass star, but it's sort of like the singular one there. Here you've got a collection of 9 of them under study, and it provides a really good laboratory for studying these very rare stars. So here, there be monster stars in R136 in the Tarantula Nebula in the Large Magellanic Cloud. Okay, now we go to our featured speaker. And our speaker tonight is Dr. Rachel Osten. She's an associate astronomer here at the Space Telescope Science Institute. And she has been fascinated by stars while she was at, undergraduate at Harvard. Her graduate school was at the University of Colorado and did post them. Okay? Our speaker tonight is Rachel Osten, and her talk is why we need to understand stars to find the next Earth. Looking for planets is not just looking for planets. Upcoming next month, we have a special talk, okay? If you were here last month, you know that I announced that Tom Brown would be speaking in May. I got Tom to postpone it because we have a special visitor. Sandy Faber from the University of California at Santa Cruz is coming for a special visit, and she has agreed to give a public lecture for us with a most intriguing title, Cosmic Knowledge and the Long-Term Strategy of the Human Race. I think when she says long-term strategy, I think she really means long-term strategy, okay? So you're not going to want to miss one. Sandy is a wonderful person. You really should come and listen to her. In June, we have Nicole Lewis, Probing Worlds Beyond Our Solar System, okay? As you all probably know, at least those of us here in the auditorium, you cannot get to the Space Telescope from the south along San Martin Drive. The south of us is closed until September, so that's still over the whole summer. You'll have to come from the north. All right, and here's a web address in case you need to look that up.
Can you tell them to say that on the signs?
Which signs? I come in from the north naturally, no matter what. So. Okay. I will tell our safety guy that some of our guests have not found the detour signs terribly illuminating, and we'll see what he can that feedback and get back to Johns Hopkins. All right. The website where you can find the upcoming lectures, you can have the link to the live webcast online, as well as the archives once we record these lectures and put them up on our YouTube playlist and on our STSA webcast. Here are the links here. If you want to sign up for our email announcements, you could do so here. We put this up just about a month or so ago, and the number of subscriptions to our email list has exploded since then. So every day I'm getting new messages of people signing up. So thank you all for signing up. I hope to keep you informed. Announcements. Signing up on our website is easiest, but if you really want to use, you can go to maillist.stsci.edu. It's called Public Lecture Announce. If you would like to contact us from the Spitzer Space Telescope, and you can see that some of it remains dark, yes, because some of it's really dense dust there that's blocking light, even infrared light, but there is a lot of glow that you can see in infrared light. Now, one problem with Spitzer is that while it has the infrared wavelengths to view in toward the center of the galaxy, it also has a relatively small mirror. Spitzer's mirror is only 0.85 meters, while Hubble is 2.4 meters. And the resolution at a given wavelength is proportional to the size of the mirror. So Spitzer can't see the details in the galactic center as we would like. Hubble does do a bit of near-infrared observations, so Hubble can see a bit more detail. Hubble and Spitzer have previously, in 2009, done an image of the galactic center region. All right, and this is the galactic center area here. This whole region, part of this image is from Hubble, and part of this image is from Spitzer. The high-resolution stuff from Hubble, some of the details are from Spitzer. However, we have a new infrared instrument that we put on in the Servicing Mission 4, Wide Field Camera 3. It has great resolution, so we looked at this region in here really close, and this is your image that we got of the galactic center. Great detail. It's near infrared. All right, and what's really cool about it is, that there's lots and lots of stars. All right, yes. It's full of stars, as the quote 2001. But right here, there is a star cluster, a really, really big star cluster. Let me set your expectations, okay? So we think of star clusters like the Pleiades, right? This is sometimes called the Seven Sisters. However, if you look, you can tell there's a lot more than 7 stars there. The Seven Sisters actually contains about 50 stars, okay? So some star clusters have tens of stars. Then we have an open star cluster called, I forget the name of it, like NGC 295 or something like that. One of these catalog numbers that you can't always remember. And you can see this one has, perhaps thousands of stars. And then you get to the really big star clusters, the globular star clusters. This one is M13, and this one can have 100,000 stars. Well, the star cluster at the center of our galaxy, this is a zoom in to see the detail. They believe it contains about 10 million stars. Okay? 10 million stars. And so we cannot see all 10 million stars here. This is sort of just the tip of the iceberg, as they said in the press release, that we're just seeing the tip of the iceberg in terms of the incredible number. The stellar density is such as if there were 1 million stars between us and Alpha Centauri. Okay? The nearest star to the sun, if there were 1 million stars in that volume, that would be the density, equivalent to the density of this star cluster at the galactic center. So as I said, we're only seeing the tip of the iceberg. How are we going to see more? Well, we need something with the high resolution of Hubble, but we need not just the near-infrared observations, we need further into the infrared. So as is sort of contractually obligated here, we must note that go from Spitzer in the infrared to Hubble in the visible to the James Webb with a much bigger mirror, keeping and getting even better resolution than Hubble at the same wavelengths, but Hubble resolution well into the infrared. The infrared telescope of the James Webb Space Telescope will be able to do that image and see much more of that iceberg. Even James Webb won't be able to see everything in there because there's just a lot of stuff in the way for seeing this. So that's what is there in the center of our galaxy. And it's much more fun instead of just doing images, you put it into a movie. So this is a movie put together by our outreach staff. There you see the teapot and the rest of Sagittarius there. And as we zoom in, he's going to crossfade to the digitized sky survey and then to that Spitzer image. and then zoom into that star cluster, and finally to the wide field camera 3 image of the galactic center. All right, question.
How far are we ballpark from the center of our galaxy?
We're about 27,000 light years from the center of our galaxy. We used to think that we're about halfway out in the disk. The disk is about 50,000 light years, about 100,000 light years across. We're just a little more than halfway out in it, okay? Cool. All right, our second story tonight. Here there be monsters. Now, of course, we're used to that phrase related to maps, and if you go off the edge of the map, oh, you get to all the monsters, and the monsters will eat your ships as you fly, or either you'll just fall off the edge of the earth, right? Well, we're not talking about those type of monsters, but we are taking a look at the Large Magellanic Cloud, and the same place where there was a monster in that last image, there's a monster in this image.